So this should be a pretty, hopefully, high level, hopefully not too, intense talk about some different topics, but mostly focusing at a bit of a high level on the Aurora GPT project here at Argonne National Lab, and in particular some of the things we've been working on, what some of the different teams do, and kind of what we've done so far and what we plan to do going forward. So I gave another, at the virtual week 2 weeks ago, I had given another talk that was also on large language models on Aurora, that was a bit more hands-on focused and looked at specific examples of pre-training, fine-tuning, and evaluating different large language models. And so there's a link here that's the kind of previous talk that I gave as part of this Insight Hackathon. So it has some good examples if people are interested. And if I have maybe a bit of time at the end and people are interested, I could go through some of those as well. So AuroraGPT. So AuroraGPT is, I guess I would say, Argonne's internal large language model development project, generally focused around kind of the high level goal of developing and building a general purpose scientific large language model that is broadly trained on a mix of scientific, text, other modalities of data. So we plan to and would like to eventually find mechanisms for including arbitrary scientific data sets. So whether that be vector-based or, how there's a bit of a uncertainty even at the moment for how to represent different data types internally in model states, and trying to figure out how to easily build a model that is able to switch between different data contexts easily and fluently is still a pretty unsolved task. And so that was kind of one of the major goals we wanted to try to incorporate from the outset. And just more generally towards pathways of building a scientific assistant. We have been working somewhat closely with researchers at Riken in Japan, the Barcelona Supercomputing Center in Barcelona, and a variety of other international partners. And this is more actually through the Trillion Parameter Consortium. So there's kind of a higher level organizational group that looks at, large language model training and trillion parameter scale models. And it's just kind of a general consortium with a bunch of different organizations that, have various meetings and things related to these ideas and topics. So that's where Riken and BSC, and there are a few other organizations that are also a part of it. We anticipate and plan to build a model that is fully multilingual, obviously starting with English being the first language, but we have plans to incorporate Japanese, French, German, and all of the rest of the generally spoken languages. And then kind of the thought or goal being that once we had a solid, have a pretty solid understanding of how to train and work with, and we've, exhausted all of the available text data that we have, we would then go on to move into, advanced scientific modalities and dealing with other representations for data and trying to have a mechanism for ingesting and generating that data back out. And so this is kind of a rough timeline. I guess, it's maybe a bit of an old figure now, but this is kind of roughly how we anticipate things to go. There's a nice little figure here that shows that it's, obviously not quantitative by any stretch of the means, but this idea that as we continue to scale up, model capacity, we seem to get these emergent phenomena. So this is a kind of interesting way of showing it, that as this tree grows, you get larger and larger model capacity, which leads to these kind of emergent behaviors that only appear at larger scales. And so really trying to tease out how that actually happens, at what scales these different behaviors are unlocked, and how to, kind of reason about and interpret these internals of model behavior are another kind of focus that we are working on. So why are we doing this in the first place, and why are we putting effort into pre-training our own large language model, given that there are publicly available and free large language models released from all of the different, large language model distributors now? So Meta has probably most popular is OpenAI's ChatGPT, which is available and free to use, but is obviously not open source. So the details of the models that OpenAI tends to use are opaque, and we have virtually no insight into the actual model, into the model itself, or the data that it was trained on. So that's probably the most extreme case. We know very little about the models that OpenAI has built and used and runs. A bit, less strict than that would be the models that maybe Facebook or Meta releases. So the Llama series of models that have been released by Meta are a good step in the open source direction. So Meta at least releases publicly all of the model weights and gives a bit of insight into the dynamics of the pre-training, but ultimately a lot of that is still opaque at the end of the day too. So Llama has been good about releasing model weights and is good about generally putting their models out into the open world, but we don't get a whole lot of insight into the many months of pre-training that it took to get there. So they generally write up the results in a blog or a paper type format, and then release it and then kind of move on without giving any more intuition about what data specifically was used or where it came from, which is ultimately a bit limiting. So if we don't have any insight into the data that a model was trained on, it's impossible for us to know if we want to then try to train that model on new data. For example, we have no way of knowing if this new data that we're giving to the model, if it's already seen it, or how unique it is from the data that it has already seen. And so without having full transparency into the end-to-end construction and creation of these large language models, you ultimately end up being a bit limited in how much you can try to reason about their ultimate behavior. And so the ideal case, what would truly be an open source model, and so there are a few companies that are following this more completely open source approach. So LNAI, for example, has released a series of models that are called OLMO, that they have done a good job about releasing the entirety of the pre-training logs and metrics and things for, which is good, but it's unfortunate that not more companies do that. And so as a result, there are kind of a lot of missing components in the publicly available large language models that we would like to try to address by training our own. So how does this look at somewhat of a high level? So the idea being that we want to try to aggregate and clean and process a variety of different data. So the starting point would obviously be text-based data. A lot of that is available from Hugging Face, which ultimately is just snapshots of the internet at different points in time that has been, subsequently cleaned up and deduplicated and things. But the bulk of the text data that was used, at least for this initial pre-training run, came from what is called the DOLMA data set that was released by OpenAI that contains a mix of these different internet text-based sources. As well as, so that's, constitutes the entirety of the text-based data set. Then we want to also try to incorporate additional modalities. So for example, we want to incorporate scientific or engineering structured data, which is kind of unique in that it is not a text-based representation, as well as, scientific papers, general text, papers, archives, papers that have been published that are kind of behind publishers' paywalls. And so there have been some behind the scenes negotiations with different publishing houses to try to make some of that paper data and otherwise protected text data available. And so we've had some success and made some progress towards aggregating and getting a variety of these different publications. That is kind of an ongoing process. Obviously, companies are a bit hesitant to if a company knows that they have some large source of data and they have all of a sudden have a bunch of people asking them for it, they are a bit skeptical to then give it out, even being the US government. But so that's kind of ongoing. And we are actually kind of always looking for new sources of data and, new ways to aggregate and host here at ALCF large quantities of text-based data that are unique from what has already been on the internet and these types of things. Also, I should have mentioned at the beginning, but at any point in any of this, if any people have questions about anything, if anything I'm saying is not clear, feel free to interrupt me. This should be hopefully pretty casual. So, okay. So what do we, all of this is kind of at a high level. What are some of the concrete things that we actually hope to achieve or get out of this effort? So a large part of this has just been, an exercise in how to do all of this. So at the moment, there are really only a handful of labs or companies in the world that are able to start from scratch, completely, aggregate and collect a large enough set of text data that they can then train a model from end to end on, and then have, the tools for deploying that and opening it up to users is actually a very non-trivial engineering task. So there was and continues to be a lot of effort based on just simply trying to get, optimal performance, making sure that things don't crash, so as I'm sure people here are now aware, working on Aurora, which is, being an Intel GPU-based system, comes with its own unique set of challenges that are maybe not the same that they would be on an NVIDIA-based system. And so all of this really amounts to a significant amount of effort into all of the engineering effort into making everything just work. So yeah, for the past year or so, a little over a year now, that is mostly what our team has been doing. So we have maintained and have this GitHub repository, Megatron DeepSpeed, hosted in the Argonne LCF organization, that has a complete implementation of our entire pre-training stack. So it has full support for arbitrary tensor, pipeline, context parallelisms, and has been pretty rigorously tested to run at scale on a variety of different, HPC clusters. So I think we've ran it just at the entirety of Aurora, as well as Frontier on AMD and Leonardo, which is an NVIDIA-based system, and a bunch of these other, non-Intel-based systems at scale, and have kind of put a pretty good amount of effort into making sure that all works, and it not only works at ALCF, but works anywhere you have access to AMD, Intel, or NVIDIA accelerator. Additionally, kind of another additional repo that we have that people have found to be useful are the inference endpoints. So Aditya, I saw, was here somewhere. There you go, right in front of me. Has been putting a ton of effort into the inference endpoints and trying to figure out and develop mechanisms for reliably serving these models to users. And yeah, so it's publicly available and works well. And Aditya is here and would love to talk to you more about it if people have more questions. But those are kind of, at least as far as I'm concerned, the two main components that I'm familiar with, at least. So the pre-training and back-end infrastructure and architecture, as well as the tools that we have for deploying it and sending it out to users. Yeah, so another important point in all of this is that we ultimately want to have a model that is useful for a scientific use case. In order to do that, there are a lot of opportunities for subtle failures that might not be immediately obvious. So it is somewhat inconsequential if your talking to a chat bot and it gives you some incoherent response. You can just ignore it, go on, whatever. But if you have an LLM or something similar being deployed in a scientific application where you have, some guarantees or expectations on numerical precision or, just general accuracy and reliability, there is, so as I'm sure people are probably aware that these large language models are not always reliable and have a tendency to hallucinate. And so will tend to say things that are just either wrong or completely made up without giving, obviously without giving you any indication that they are lying. And so that makes it then challenging for you as a user to, if this is all running in some embedded loop and you have no way of guaranteeing that your model outputs are correct and valid and accurate, it complicates things and can be a real challenge. And so trying to reliably incorporate large language models into scientific applications is a, kind of general challenge that I think a lot of people are looking at and trying to figure out. So one thing that is nice about being able to control the entirety of the pre-training, workflow is that we have explicit knowledge about all of the data that our model was trained on. And so we then have an exact record if, we finish the pre-training, say, and we fix and then distribute that model. And now users want to take that model and fine tune it on their scientific application. So I've worked with Arvind Ramanathan on using large language models for genomic data and working with genomic text data. And we would like to try to have a better understanding of how a model can how it behaves when it sees new data that it hasn't seen. So if I know that if I want to try to give it some new data that we know to be unique, we know this data was not contained in the initial pre-training data, and then evaluate the model after it's seen this new data, for example. So you could imagine giving it the new Math Olympiad from this year and then see how it does, right? And if I know that none of those questions from this year's Math Olympiad were in my pre-training data set, then I can be pretty confident or reliable about how about its evaluations from that, right? So if I know that it hasn't seen any of if I know that it's possible that it has seen some of this data, then there's no way I can make any sort of prediction about, if showing it this new data actually helped or if it just remembered something that it had seen previously. And so there are some nice benefits from doing everything yourself. But unfortunately, it's a very challenging thing. So for people who are aware, this initial pre-training phase is what usually takes generally the largest percentage of the compute used in these large language model, development and deployments. And so that takes a significant amount of engineering effort. And obviously we do not have the capacity that, say OpenAI does for building and developing these things. And so the quality of the models that we are, this is the first round we did it. We have now trained to completion a 7 billion parameter model that has been trained on 2 trillion tokens of text data. And, while we're happy with the model, capabilities for what it is, obviously it is not at the level of something that OpenAI would be able to produce. And so there's a bit of a growing, discrepancy between the quality of model that we seem to be able to produce and what is happening at the large frontier labs. And so trying to, find a way to bridge that gap or continue to work in such a way that we are able to make forward progress is going to be important. And it's all kind of, I would say, a bit up in the air at the moment. Obviously, this is a field that changes very rapidly, even day to day. And so trying to always keep up with, the new releases and these types of things is a huge challenge, especially for a team of, I don't know, I think there are like 8 or so of us, and specifically focused on the pre-training. So this is a slide that shows the details of Aurora, but you obviously all know that, and we'll, I guess, see it later today, right? Is the tour? I think saw it yesterday, so everybody already went and saw it. I guess with the new skin on it now. So it probably looks a bit different from this rendering, but hopefully everybody should be familiar with the details of Aurora. Another slide that I had stuck in here, just so that maybe people are aware if they otherwise weren't, that we here at the ALCF also host this AI testbed system. So we have a variety of different AI accelerators, Samba Nova, GraphCore, Cerebrus, and Grok accelerators that are available publicly for allocations that people can apply for time on. And so if this is something that is of interest to you, yeah, we encourage you to apply for time on these machines. And yeah, just to say that. So yeah, what is the larger organization of the AuroraGPT project, and who are some of the people that are involved? So at a very high level, these are the different team leads. So there's a planning team that is responsible for, generally organizing the project's goals and plans. The data team, which is managed by Ian, Foster, and Robert, who I don't think are here. The training team, which is managed by Venkat and I, who's around here somewhere. And a variety of other teams that I am a bit less familiar with. So here's kind of at a maybe high level what each of the different teams do. So planning, yeah, is kind of responsible for what the project is going to do. Data preparation team is the team responsible for aggregating and collecting novel text-based data sets. And so their goal is to try to accumulate an additional 20+ trillion tokens of high-quality scientific text and structured data. That is a very challenging task. So people might be surprised I don't know if anybody has ever put any effort into the actual, day-to-day work of trying to aggregate, clean, deal with text data. It's very non-trivial and frustrating. So that's what that team does. I personally help lead the models and pre-training team. So we are responsible for creating, testing, training entirely from scratch a series of models that are trained on publicly available data. And so, yeah, that is what we do, the pre-training phase. And there are also teams associated with evaluation. So being able to evaluate not only our model, but other large language models on different scientific tasks, and evaluate, their performance on a variety across a variety of different scientific disciplines on a variety of different tasks. There's also the post-training team, which is a bit more focused on the fine-tuning and alignment aspects of the large language model lifecycle. And so this actually is kind of expanded to include things like reasoning and inference time compute. So the distinctions between some of these teams maybe gets a bit muddy when you start looking at the details, but and so the inference team again is responsible for hosting the inference endpoints on ALCF, pulling and maintaining different large language models from the different providers, and making sure all of that works reliably and efficiently for users. And then the distribution team is more kind of high level focused on, the optics and how making sure that we as a team are not violating any sort of licensing or copyrighted data, and are not doing anything that would get the division in trouble more generally. And then communication, obviously, letting people know what we're doing. So I guess I'm supposed to go till 1. Okay, that's fine. So yeah, I guess I've kind of said all of this a bit out loud already now, but the data team, so obviously in order to train one of these models, you need a lot of data. And one of the major challenges is that a lot of these frontier labs seem to be accumulating significant amounts of text-based data that is not on the internet. It's not coming anywhere from the internet. And so OpenAI, for example, continues to aggregate all of your, submitted inputs and a variety. They have a whole bunch of other mechanisms for aggregating new data. And it's a, there's, without sort of that level, without like, an OpenAI's budget, it's very hard to try to find new text-based data, right? Like, we don't really have a lot of reliable mechanisms for generating new text-based data, and the text-based data that is available at the end of the day ultimately comes from some snapshot of the internet at some point in time, just, cleaned and deduplicated in various ways. And so the amount of text-based data that's on the internet is kind of more, growing smallly, but more or less kind of fixed. And so without new, data streams incoming, where do we get 20 trillion tokens? And so that's actually a very, non-trivial challenge, and has been very difficult to actually do in practice. Another kind of challenging part of all of this is that we want to focus on scientific applications in different scientific domains. In order to do that, we need scientific domain experts to, obviously I don't know everything about, say, computational astrophysics, for example. And so I am not going to be able to reliably create new, astrophysics data set, questions or answers, and I don't have the necessary knowledge to be able to evaluate if the model is speaking, truthfully about these types of things. And so then that requires then pulling in somebody who does know the specifics of that. And people are busy, don't really want to, spend their time answering questions for something that they're not a part of. And so trying to get domain scientists involved in such a way that, it's useful for us and not a waste of time for them has been challenging. And yeah, so that's definitely very much ongoing. One maybe concrete thing that might be kind of interesting, since this is the GPU hackathon and we are interested in HPC performance and making sure all of our codes run efficiently. We'll talk a bit through one of the immediate challenges that we had when we first started this entire process. So yeah, as we initially started, we had this goal. We wanted to train our model on 2 trillion tokens. And so the first step in all of that involves aggregating, sampling, and building these indices to the data. So every time I want to, do a training run, say, for example, I want to try, 32 layers or 36 layers and see how my performance is, right? Because you have to do this kind of like exploratory kind of analysis at the beginning to find a sweet spot in terms of model performance and throughput. And so you want to, as we were initially kind of starting up, we wanted to run a bunch of different experiments, just to kind of better understand things. But in order to do that with 2 trillion tokens, each time we went to start the training run, the logic just behaved in such a way that you have to explicitly, for each of those 2 trillion tokens, you have to figure out, where it is on the file system and what batch I plan to use it in. Once I know what batch I plan to use it in, then I can kind of, enumerate out for each step where all of the data in that step is coming from explicitly. And I need to do that for all 2 trillion tokens, right? Because if I want to stop and resume this training at any point in the future, I need to be able to know where I left off and, pick back up from there. And so this involves this kind of building of indices that explicitly map tokens to their locations on the file system. And this original implementation was very slow. So it took roughly so in the original implementation, this would all happen serially. So it would, for, token number 1, token number 2 for all 2 trillion tokens. So obviously this is not, ideal, and this is very slow and really prevented us from rapidly iterating on our experiments. And so what we did was completely rewrote all of that logic and wrote it in such a way that it is now distributed over all of the available GPUs that we're working on. And it does it kind of asynchronously now. So it cut down the time spent doing this from about an hour initially to under 2 minutes. So that was a huge win and allowed us to obviously then, if I only have to wait 2 minutes for each new experiment to start up instead of an hour, it allows me to try many more experiments much more quickly. And so this was actually a huge, kind of win for us that Huiho is here somewhere, kind of spearheaded and led. And yeah, we've been working with the Deep Speed team from Microsoft on getting all of these features merged into their Deep Speed library. And so, yeah, this was kind of a huge win that, yeah, was good for us. But then, so once we had kind of gotten past that, we still, as you might expect, faced a variety of other challenges. So when we are doing these large distributed kind of sustained pre-training runs, we really want them to be as efficient as possible. When you're running on thousands of GPUs, even a small improvement in throughput can result in a pretty significant amount of compute reduction needed. And so we really want these all to be as efficient as possible, as well as stable and reproducible, obviously. So as far as runs being stable, that is, I would say, still, a major challenge for anybody that is trying to do a large, just, sustained training run. Nodes break, GPUs fail, networks time out. And so when something like that happens, it usually has the effect of completely crashing your training run. So if you have, 1,000 GPUs up and running, and then all of a sudden one of them hits a snag, it'll kill the entire job, and all 999 of the rest of them will crash. And then when you want to try to recover or restart from that, you have to then redo all of that initialization logic. And that can be quite expensive depending on the specifics. And so being able to quickly recover from individual node or GPU failures is a huge challenge that only grows at larger scales. So as you have more and more devices, the likelihood that any one of them will fail also grows. And so being able to reliably kind of reason about, training and model and system stability is difficult. And yeah, so in order really for any of this to happen, it all relies very heavily on having robust data pipelines and file IO operations, being able to effectively overlap compute and communication, especially on the new Intel devices has required a bit of effort. We're also interested in looking at things like large batch training and second order optimizers, which have the potential to significantly speed up these training runs. And ultimately, all of it relies on having highly optimized GPU kernels to actually drive the back-end matrix multiplications. But what we actually see in practice is that it's very challenging. And so for these runs that we anticipate to span many weeks or even months, you really kind of need to have it pretty well planned out. You want to try to use that enormous amount of compute as responsibly as you can, obviously. And this is a challenge when you have individual jobs that are fragile. So as I mentioned earlier, if you have a single rank or a single worker go down at any point in the training, that will, at the moment, currently cause the entire run to crash, which then causes you to then have to restart from roll back to the last checkpoint, do all of the initialization again, and then restart the training, which is, in practice, a real challenge. Another consequence of all of this is that your training run can only ever proceed as fast as your slowest worker. So if you have a system that has high variability between ranks, even just trying to figure out why that is the case, or trying to make sure that all of your workers perform in lockstep operations can be useful. So on Intel and Aurora specifically, being a 10,000 node machine, there are a lot of challenges that only seem to appear at those large scales. And so as a result of that, there are a variety of different kind of behind the scenes algorithms for doing these, collective communication operations. And so really just even trying to fully understand, how they're implemented, how we anticipate them to behave under different situations, and trying to build some intuition and reasoning about, how different environment variables can affect collectives and when to use certain ones versus not. all on top of everything else, just really proves to be very challenging. And so this is, what we spent the better part of the last year working on and trying to figure out. So this is about evaluating foundation model skills for science. So, at the end of the day, all of this is a waste of time if our models are completely wrong, right? Or if they're not giving us information that is useful. And so in all of this, we want to always make sure that anything that, results or, things are backed up by some sort of ground truth. And so we want to have ways for, precisely measuring how well a model performs on a given task, for example. And so building and developing these sort of evaluation, questions or pipelines or, criteria for models is a very active challenge, especially as they continue to get better and better. It's becoming more and more challenging to come up with questions that are, sufficiently novel and challenging to them. So the general research direction of building benchmarks and reliably reliably evaluating these models is changing very rapidly, I would say. I guess even for along that point, there was, I guess, some controversy recently about, maybe not controversy, but there's some speculation about whether or not some of these more recent models may have included, these evaluation criteria in their training data. So I think the software engineering benchmark in particular is kind of known now to be corrupted. And so once if you have some existing mechanism for evaluating these models that eventually creeps into their training sets, then they've seen it all already by the time that they're being evaluated, right? If I know in advance what's going to be on the test, it makes it much easier for me to do well on the test. And so as the existing benchmarks and evaluation criteria have kind of, seeped their way into these models' training data, the results of their benchmarks are become less reliable. And it just becomes very, at that point, very easy to try to game the system in such a way that, you do really well on all of the benchmarks, but then in real world use cases, your model is actually not that good. And so trying to find ways to prevent that and, deal with that reliably is a challenge. Like I said before, wanting facts to be correct and accurate. We also want them to be reliable. So you want, given, if you ask the model the same question multiple times, you want it to always give you back out the same response. And a lot of the details and how that is all done is, again, all of this is very much in development and trying to be figured out by not only us, but a lot of teams otherwhere. So I guess then, I guess that was about all I had for high level things. So I have now a few kind of performance scaling results. So this chart here is from a paper that we submitted last year to supercomputing. So it was a finalist for the Gordon Bell Award last year that looked at using direct preference optimization for multimodal protein design workflows. And it uses our pre-training stack. It uses the Megatron DeepSpeed repository that we have. And this MPro DPO workflow was ran on a variety of different accelerators. So Aurora here at ALCF, obviously, ALPS in Switzerland, which is NVIDIA, I believe, or maybe AMD. Leonardo and PDX, which is PDX and Leonardo, which are both NVIDIA. PDX is an internal NVIDIA cluster, and Leonardo is a new supercomputer in Italy, I believe, in the Italy Supercomputing Center. And so, we saw very good scaling results on all of these machines, and we're able to get up to about 40,000 GPUs on Aurora and achieved a little over 4 exaflops of sustained performance. So that was really good, we thought. And there are a lot of other details about the workflow in the paper, obviously, if people are interested in reading more. But yeah, so that was a pretty well-received result. I think there are some other, a lot of the people from the team are also here, so I don't mean to take all the credit, but yeah, this was I would say a very good result. We had good performance. The scientific case was strong, and yeah, has been a very fruitful kind of research direction. I won't really talk about that actually because they are all here. Yeah, and then I've got a bunch more links if people are interested. But that was kind of about all I had for high-level talks, and I'm about at the top of the hour. So if anybody has any questions about any of this, or would like to talk about anything that I've talked about, yeah, feel free to reach out. I'm here, available, happy to talk anytime.
Thanks, Sam. So I have one question. Can
Sure.
people access the AuroraGPT outside of Argonne, or is it still within Argonne?
I think it's a good question. So so we have now trained and distributed, well, not distributed. We have the AuroraGPT 7 billion parameter model is up on Hugging Face, but it's currently in a private organization that, yeah, anybody that's ALCF that were to want access to it, I think, so I am an admin on the space and can give you access, I believe.
So ALCF only, not Argonne only?
So we want to release it publicly and have it be just publicly, openly available. Eventually, if it were up to me, I would let people have it, but I'm not in charge of those decisions. And so as far as I'm aware, anybody at Argonne, I can't see an issue with them having access to it. So yeah, if anybody is interested in getting access to it, reach out to me and I can, double check with the powers that be and see if we can get you access. So okay, okay, so that's right. It is actually hosted on, so the AuroraGPT 7 billion parameter model is actually hosted on the inference endpoint at ALCF. So anybody who has access to the ALCF, has an ALCF account and can use the inference endpoints. Oh, even in Argonne, anybody with an Argonne account can use these inference endpoints, and on the inference endpoints, you can select the AuroraGPT model. So yeah, if people want to play with it, you can get to it from the inference endpoints. But if people are interested in getting more, actually getting access to the model and the model weight specifically, let me know and I can make it happen.
I think that would be interesting. Okay, well, thank you, Sam. Are there any questions or comments about the AuroraGPT or LLM models in general?
So in computer science, at least, the model that is trained on all the PDFs from ACM and IEEE would be really very interesting to our computer scientists. Are there any plans to reach out to these organizations and train on their complete archive? Because just everything else is not quite there.
That's a very good question. And I thought I had, okay, yes. So yes, the question was, it would be interesting to have access to all of the ACM and IEEE, locked publication, all of the text from their publications. And yeah, there is a pretty, you would imagine a pretty large quality source of text data. And so we have been in contact, and I think we've gotten, so I don't want to misspeak, but I believe that we have worked out an agreement with ACM. And I know that we have at least struck a few different agreements with different publishers that have now granted us access to their, otherwise blocked publications. Yeah, I don't see anybody from the data team here who would be able to talk more about it. But I know that it's something that we are very, very actively pursuing, and is tough because now they all realize that they have, now they all realize they're sitting on a gold mine. If originally it was very much like, oh yeah, absolutely, we want to let people have this data. Then they kind of a lot of them realized that they were actually sitting on a gold mine, and have since clammed up and are now a lot less, willing to engage in, from what I have heard. And And so, yes, trying to get that data source, get those data sources and work with it is very much ongoing. And I don't know if we have a definitive one way or another yet.
Do you know if any commercial partners like OpenAI are also
I think
pursuing that?
I believe that I've heard that OpenAI has, OpenAI at least I believe has like, from what I have heard they have done a good job of wooing the publishers to give them their data. From what
So they have trained on that?
Being here on the spot, I'm pretty sure that I don't work for it, but I have heard, I at least have heard that OpenAI at least has access to a lot of data that other people otherwise do not.
Thank you.